Beam me up, Scotty. When we hear the keyword teleportation, we often think of miraculous technologies that instantly transport matter from one place to another at the push of a button, but while the fiction shown to us in Star Trek and the like is physically impossible, quantum teleportation describes a process that has long since arrived in reality. In detail, we are dealing here with the transfer of quantum information such as the spin state of an atom, which is transferred to a distant second atom. Quantum teleportation does not transfer matter but only its stored information, and indeed experts have recently succeeded in achieving some groundbreaking milestones in this exciting field. For example, there are the scientists at the Max Planck Institute for Quantum Optics who have developed a method that is as simple as it is groundbreaking, requiring only a single photon as a transmission resource, or the Chinese researchers who have established a quantum link via satellite between ground stations 1,200 kilometers apart. What Mario Kart or Monopoly is for us, quantum physics was for Albert Einstein and Niels Bohr. Although the two physics luminaries were actually good friends, they repeatedly engaged in heated discussions about the question of whether different basic principles apply in the mysterious world of quanta than in our everyday world. One of their main points of contention was whether two quantum particles can still be in a shared state even when they are far apart, or whether each particle carries its own individual state. In the first case, which Bohr argued for, both particles would be entangled, or in other words linked to each other regardless of their locations and distances. In this context, any measurement that changes the state of one particle would also have an immediate effect on the state of the other entangled particle. In this case, which Einstein advocated, however, both particle states would be fixed from the outset, and a measurement on one of the particles could only influence the other if a message were transmitted, and that was precisely the crux of the matter for Einstein. According to the special theory of relativity, such a signal can travel at most at the speed of light, so it would necessarily take a certain amount of time to travel and could not be passed on without delay. The bottom line is that Einstein did not believe in the phenomenon he once famously referred to as spooky action at a distance, and was thus dramatically mistaken. In fact, the predictions of quantum mechanics have now been successfully confirmed by experiments. In detail, all tests carried out so far have confirmed B's assessment that the quantum world involves non-local interactions, which is why quantum entanglement is no longer considered an exotic idea but a recognized physical phenomenon. Quantum entanglement over 1,200 kilometers. However, the highly complex experiments that provided the proof of quantum entanglement were not carried out until decades after Einstein and Bohr's deaths, so we can only speculate about how the creator of the theory of relativity would have reacted to the groundbreaking demonstration that Chinese physicists carried out a few years ago. As already mentioned, any change in the state of an entangled photon also causes a change in the state of its partner, so that information can be transmitted instantaneously, or in other words without delay, over enormous distances. And yet this phenomenon also has a crucial limitation in our earthly environment, because in both the glass fiber and the Earth's atmosphere, disruptive effects ensure that only a few photons arrive at their destination in the entangled state, and so it was that the maximum range of this quantum communication was just 100 kilometers in the run-up to the Chinese experiment. But in the vastness of space, the photon pairs are much less disturbed, since the entangled photons travel through the vacuum of space for most of their journey. They remain entangled even when sent to two ground stations far apart, and the Chinese research satellite Maiyu's impressively demonstrated that this theoretical approach also works in practice. It succeeded in sending entangled photons to two receiver stations in China that were no less than 123 km apart. But how does something like this work? Well, when it comes to the technical details, the transmission unit of the quantum experiment on board the satellite comprised a laser whose beam was guided through a waveguide and a special crystal. In this way, 5.9 million entangled photon pairs with a wavelength of 810 nm were created per second. The entanglements in turn affected the polarization state of the pairs. In simple terms, the direction of their vibration. The satellite's attached telescope dish then took on the task of sending the two beams of entangled laser photons to a ground station, and with resounding success, the ground stations were to receive the satellite's beams without the photons losing their entanglement, and that Despite the fact that the pairs were sent to Earth from an altitude of 500 kilometers and depending on the position of the satellite had to travel up to 2,000 kilometers, another challenge was the high speed of the satellite since it was constantly moving in relation to the ground stations. The transmitting and receiving systems had to follow its movement as precisely as possible. Despite all this, however, the transmission was powerful, full enough to read the transmitted information and thus form the world's first orbital planetary quantum network, a completely new approach to quantum teleportation. Did Einstein and Bohr ever imagine that their scientific successors would one day venture into space to find the answer to their dispute? Well, who knows? What is certain, however, is that in principle no quantum teleportation is needed at all to transmit quantum information over long distances. To do this, a qubit, a small quantum information store, can simply be encoded in the direction of oscillation of a photon, which is then sent through an optical fiber and can thus in principle send the information back and forth between two distant locations. However, because photons are very fragile and fleeting, they are easily lost along the way, and with them the stored quantum information. Quantum teleportation can circumvent this problem, but to put it mildly, it's challenging. After all, it requires two entangled particles in advance to serve as a resource for teleportation, and such a resource is usually anything but easy to produce. In this context, the team led by Stephen W. Stefan Langenfeld and Gerard R. from the Max Planck Institute of Quantum Optics wondered how it would be possible to carry out quantum teleportation using a more readily available resource, namely with just a single photon as an auxiliary particle. Published in Physical Review Letters, the series of experiments was based on individual cooled atoms and the principles of cavity quantum electrodynamics and ultimately resulted in a completely novel procedure that uses just a single photon to teleport the spin state of a single atomic qubit to a second atom 60 m away. The qubit to be teleported was trapped in an optical resonator, while the second atom was also trapped in a resonator in a neighboring laboratory. To transfer the information, the scientists reflected a photon sequentially at the two resonators in which the two atoms were located. The photon flew through an optical fiber connected to the two resonators, and then a measurement of the photon and the spin state of the first atom was carried out. Based on these two measurements, a feedback signal was then sent to the second atom, which was irradiated as a laser pulse and whose properties depended on the previous measurements. All in all, this method allowed the information to be teleported from one atom to the other. But if we just let our thoughts run free at this point, another exciting question arises. After all, isn't it possible that quantum teleportation ultimately offers some loophole that also makes it possible to beam people? The dream of beaming? Well, to start with, it's important to keep in mind that strictly speaking, the information in quantum teleportation doesn't travel from point A to point B, rather it appears at point B and disappears at point A when you read it. Furthermore, the amount of information that can be transmitted in this way is extremely limited, usually only a few bits. Furthermore, a major hurdle is that one of the two entangled particles must always be brought to the destination first. In order to teleport information, only when the coupled particles are in place can the information be shared between the sender and the receiver without delay. And if you want us to bring our videos into your reality on a regular basis, then simply click the subscribe button. We'd be happy to have you join our community so you never miss a new post from us. Again, we'll see you soon.